Is this on? Yeah, I think it is. No? But it says green here.
Oh, okay.
There's on the top.
No, it is green.
You just have to have it
I think I might have to
too far away, just like
too far away.
Yeah. But yeah, we'll wait a couple of minutes.
Yeah. Did you rescue your keys? Okay.
It's because since I need to switch with Alberto,
I see.
I wanted to be prepared so that
Okay,
you know,
yeah.
you don't need to wait for
No.
So you are going to lunch with Alberto and Jonathan?
Jonathan's here. I just met him. Yeah.
And yeah, so you will meet Alberto just outside.
Yeah, I'll figure out. I'll go with him. Yeah. We'll figure out. Hi.
Okay, my introduction
No,
for...
it's short. Keep it short. Oh, so he didn't. Oh, I.
Yeah, we didn't need
Okay.
that, yeah.
Yeah, so I can hang out, but if you guys have things, then there's no
Oh, no.
pressure. Yeah.
I'm going to go to dinner with you, so I'll take you over.
Yeah, we can meet a bit earlier. Yeah. So something.
Is it okay if Helen comes to dinner?
Yeah,
Is it
of
okay if
course,
Helen comes
yeah.
to dinner?
Oh,
I'll
yeah,
make
that'll be
reservations.
great.
We're going to go to Everly. Is that
Yes,
okay? Or
yeah,
somewhere
it's
else?
okay, yeah.
Yeah, I
Maybe
like
we
that.
need to... I
I'll
don't
talk
know.
to Cassandra.
Yeah, I don't know if to switch with Alberto or if Shantanu proposed that we bring the kids, but I don't want to disrupt the dinner. So yeah.
Oh, no, you should. Okay, so whatever you want, yeah.
Yeah, but definitely.
Or we can just go someplace else, too. There's lots of places.
Maybe there is space.
Okay.
Yeah, we can whatever. Yeah, it'll be fun. Yeah, we
I'll
can.
talk to Cassandra.
Yeah.
I mean, I think just ask to add Ellen, which anyways, 3 versus 4 is not going to change much. I'm not sure if I bring the kids because I fear that then it gets too much.
A little chaotic.
You can stop by at our place.
Yeah, no, it's fine. Next time. Yeah. Okay, we can start.
Okay, good morning, everybody. Welcome to our colloquium. So today we have Professor Santanu S, who is a professor in the School of Industrial and Systems Engineering at Georgia Tech. So he's one of the most prominent researchers in discrete optimization, especially in the area of mixed integer linear and nonlinear programming. He's interested also in applications, for example, power systems, logistics and statistics. He has received many recognitions and awards, among others the NSF Career Award and the Informs Optimization Society Ballas Prize. So we are really happy to have him here, and please join me in welcoming Professor Day. Thank you.
Thank you very much. You can hear me. Usually you should be able to hear me. That's the only reason I'm prominent. I'm loud and big, so you can see me from far off. Thank you very much for this invitation. And it's really great to be here with friends that I hold really dearly, both scientifically and as friends. And also some of the stuff that I'm presenting, actually the experts are here, the world experts, so I'm hoping to hear from them. So today I'm going to talk about some duals for integer programs. I really like duals, and so maybe what I'm talking to you about may not look, feel, smell like a dual, but that's okay. I like duals. I'm going to call them duals. This is joint work with my colleague Diego Cifuentes, with Marco Molinaro, who has been my partner in crime for the last 12, 15 years. We work a lot together. He's in Brazil, also works in Microsoft. Xiaozhe Wang, who's a master's student, and really the thought leader for a lot of what I'm presenting is Jingye Xu, who's a PhD student in his 3rd year. All right. Okay, so this is, okay. So So there's actually a very people don't think, people think about, when people think about duality, they think about convex optimization, and there's of course a very beautiful theory there of duality, but really it turns out integer programming also has a very literature of duals and strong duals. And I would say the only difference, I would say, and I'm not an expert really in convex optimization. Do I have to be close, maybe? I have to be close. I would say the distinction between the dual theory in IP and convex optimization is, I feel like a lot of the proofs in the convex optimization tend to be somehow, at the end of the day, related to some separation theorem, separation of convex, point from a convex set type of thing. But in integer programming, I think there are lots of different types of duals. And in a way, they are based on different structural properties, but they also have been designed for different reasons, right? They have different purposes in some sense. Right? So as an example, like one of my most super favorite, anyone who knows me knows that I love this, is the subadditive dual. And this talk has got nothing to do with subadditivity, but I always try to sneak in subadditivity. I like it. And this dual was somehow, you don't think of it as a dual, but it's really a dual. And it's a dual because it was designed, you can think about it as a way to explain cutting plane theory in integer programming. Really, it's the theory behind cutting plane. And there was this other tool that I really like, which was Natasha Boland and then Shabir Ahmed and collaborators worked on, which is the augmented Lagrangian dual. So I won't have time to talk about these duals, but the augmented Lagrangian dual, for example, the purpose of doing this was to try and design ADMM-style algorithms for integer programming, which we know we can do for convex optimization. Right? So I'm going to be talking about two new duals that we have worked on in the last 2-3 years. These are not as general, so they don't hold for general integers, but they hold for binary IPs. And they also have been designed using completely different properties, you will see. One is in order to try and do distributed computing for integer programs, and the other one is to do sensitivity analysis. Right? I will primarily focus on, I think this is, so I'm going to primarily focus on the first one. Sorry. The first one, and if I have time, I'll do the second one. But let's see. Hopefully, we'll get to both of them. So let's talk about the first dual. All right? So the Lagrangian-Stroll dual. So for this part of the talk, I'm going to focus on this sort of quote-unquote toy problem. Okay, what is this toy problem? So you have these two x's. These are two mixed integer linear sets. Okay, so for now, linear, we can do nonlinear. But these are variables, x's and y's, 1 living in x1, 2 living in 2. And you can think of these variables, satisfying some integrality conditions and some linear inequalities. And for each of these two sets, there are two linear objective functions, right, 1 and 2. So if you disregard this, I believe this is purple. If you disregard this line here, I have two different IPs. Their own copy of variables and their own feasible regions, their own objectives, right? What makes this problem interesting is this additional constraint, which is a coupling constraint, which says that a subset of variables from the first guy and the subset of variables from the second guy have to be equal, okay? And this seems like a toy example, and it is a toy example in some sense, but I'll discuss later why this is actually fairly general, and it comes up in a lot of different applications in different ways. One thing that is going to be useful and important for a lot of our results is that these coupling constraints that says maybe the first 10 variables of the first problem and the second 10 variables of the second problem, they have to be exactly equal. These coupling variables have to be binary. A lot of what I'm saying, the proof techniques will go through even if they're not binary, but the final results, the clean results, only work when they are binary. Okay? As I said, we will look at more, this is sort of simple. I will talk a little bit more about more general things later. And obviously, the experts here are seeing that this is really a basic example, for example, for two-stage stochastic programming, where you can think of these x's being your first stage variable, or also the state variables. And you can think of these y's as your second stage variables, right? Is the setup clear? Is there any question here? Very simple, right? I have two IPs that are completely, they have got nothing to do with each other. They have their own variables, their own objectives, their own feasible sets. But then I additionally say the first 10 variables of this guy and the second 10 variables of these guys, they have to be equal. Okay, good. All right. So what do I do to solve this problem? Of course, the first thing that you would do is say that, if I want to really use the structure of the fact that there were really two different constraints and I just had this one additional coupling constraint, is to just throw away the coupling constraints. I can do that, and I will definitely get a bound. All right, I'll get a lower bound of the problem because I'm relaxing the problem. But this bound may not be the best thing that you can get. And what is sort of the standard thing in the literature that you do is you do what is called a Lagrangian decomposition. Right? So instead of completely discarding these couplet constraints, you say, I'm just going to put them in the objective, and I'm going to put a penalty with them. Right? For any value of lambda, this problem is well defined. And what is nice about this problem is because this was a linear equation, and this is sort of linear, for a fixed value of lambda, these two terms separate, and so again, I get two separable problems. Is this clear? And then it's clear that the value of this is a relaxation of this problem, and so I can search over the lambda parameters to get the best lower bound. And this is the Lagrangian dual. This clear? So what are the nice things about the Lagrangian dual? The nice things about the Lagrangian dual is that, as I said again, this expression in lambda is again separable. So because you've removed the constraint to the objective and this is all linear, for a fixed value of lambda, this separates into two problems I can solve separately. So I can do decomposition. But what is even nicer is it turns out under very general conditions, these don't have to be mixed integer linear sets. These don't have to be linear objectives. You could have pretty much any kind of crazy non-convexity, discreteness going on. This function will always be concave. And what is more, for a fixed value of lambda, it's very easy to actually, well, quote unquote, easy to find a subgradient for this concave function. You just solve this expression, you take the optimal solutions, and in this very particular setting, you take the difference of the optimal solution of the first subproblem, second subproblem, it turns out that vector is a subgradient. And the convex optimizers have done a great job coming up with all these family of instances, algorithms like subgradient and bundle, and so you can optimize on this. So this is a really nice method because, as I said, once you dualize the objective, the problem still decomposes. So I can do this parallel computation. And because this function is concave on the lambda space, and I can find these subgradients very well, I can do like a subgradient algorithm. Right? So I can do a subgradient algorithm at the top, and at each time, I just do parallel IP computations. So that's very nice. So what is not so nice? Or maybe first, let me tell you a very nice theorem about this. Again, there are experts in this room who know much better than me on this topic. So this problem here has these lambda variables, and there is this problem, subproblem, and then the sort of Lagrangian dual, finding the best penalty terms. But it turns out you can clean up all this and you can tell exactly what is the bound you get using this Lagrangian dual in the space of the original variables. So there's no lambdas here, and this is sometimes called as a primal characterization. There's a theorem by Geoffrion that says that what is the value you get by solving the Lagrangian dual? Well, the value you get is optimizing precisely the same objective that you had on the same sets of variables you had. What is your feasible region? The feasible region is you're convexifying each of these squiggly x sets separately, and then you add this x1 equals to x2 outside of the convexification. Okay? And I see some people nodding their head, and I think it's clear to everyone this is not the original IP. And why is it not the original IP? Because remember, our objective is linear, right? So whenever you are optimizing a linear function over a set, it's the same as optimizing linear function over the convex hull of the set. So in order to compare this to what we are really doing, our IP is solving the same linear function over what? Over the convex hull of each of these copies of variable living in their feasible set, and x1 equals to x2, and then you take the whole thing and do the convex hull. But here, this x1, x2 is outside. And because of this, you don't get a strong bound. You get a good bound, and empirically you get great bounds. But do you actually close the gap? The answer is no. Okay? And again, if you've never seen this before, let me give a very quick example. So imagine that in the sort of x space, my first squiggly set, the feasible points were 0, 1, and 1, 0, so the red guy is here. And the other set, the feasible points were 0, 0, 1, 1, right? So if I enforce x1 is equals to x2, then in fact this problem is infeasible, right? The red guys and the black guys are totally different, so there is no conversation. But when I solve the Lagrangian dual, what Jeffreys theorem tells me is that what is the bound I will get? The bound I will get is basically first I will convexify this set, right? In other words, I will take this red guy, and draw the line segment between them. I'll convexify these 2 points, so I'll draw this. And then I will add this equality constraint on the outside, so I'll take the intersection of these 2 convex hull, and I'll get this green point. All right? So the original problem was infeasible, but if I used this sort of Lagrangian dual, I would say that actually the problem is feasible, and I'll actually find a feasible solution, right? And so therefore, clearly, this is an example where the gap is infinite. So in general, it's not surprising you have a gap. All right, very good. So what is our goal? Of course, I gave you this problem where there were 2 individual IPs, and I said the first 10 variables here have to be equal to these second 10 variables. I just say, look, I don't know anything, I can just solve the whole problem. Give it to your favorite solver, that's great, there's no gap, that's a sort of a trivial statement, but then I'm completely disregarding the block structure. I'm not going to be doing any decomposition. Or I could, for example, use the Lagrangian decomposition we just talked about, where you get this beautiful algorithm that uses this block structure that allows for decomposition, but there will be a gap, right? As we just explained, the optimal value from this Lagrangian dual will be, in minimization case, might be lower than the actual IP value, and there'll be a gap. Is this clear? And so, of course, we are greedy, and we want both. So we want a method where we can decompose, but we don't want a gap. So we want a method where, most of the algorithm steps are done in decomposition, sort of in the separate space of the 2 sets of problems, but eventually I get a complete type bomb. Okay? And this is what I call as a strong dual. All right, so let's construct this strong dual. What is the main idea? So the key idea, and I think this is probably, if you had to take away anything from this part of the talk, is what we do is we add redundant constraints of very particular form, right? So what we are going to do is we are going to add, and I'm going to give an example in a second, so this is a little written in a slightly abstract way. I'm going to first think of inequalities that are implied by the fact that this string of binary vectors was exactly equals to this string of binary vectors. And I'm going to think of these redundant inequalities of a very particular form. It will be some function applied to the first string plus some function applied to the second string, but I would want this plus. And you'll see in a second why I want it this way. Okay, and some inequality like this. Well, okay, so this is very abstract. So what do I mean with this? Let me give a specific example. So I need these 2 strings to be equal. They are binary vectors. In other words, this variable, I want it to be equal to this variable. I want 2 of the first vector to be 2 of the second vector. So because they're binary, you see that this is true, because this was equal to this is equal to this. Sum of these 2 numbers is greater than or equal to the product. Is this clear? So this sum here is my alpha 1 function, and this product here is my alpha 2. And they have, okay, here I have a minus, but you know what I mean. It's plus, right? So they are separable. So I'm applying some function to these guys, applying some function to these guys, and this is completely implied by the fact that these 2 were equal and they're binary. Okay? So what I can do is I can take this redundant constraint and add it to my problem. Actually, I've not changed anything to my problem, right? Because it's just a redundant constraint implied by these guys. So with this, let me denote the updated problem with a sort of a tick mark here. Clearly, the optimal solution and the optimal objective value of the 2 problems have not changed at all. But then the question is, what happens to the dual? Right? So now I have this additional redundant constraint. So when I take the Lagrangian dual, this was my original penalty where I was saying these 2 have to be equal. But I'm going to take now another dual variable corresponding to this redundant constraint and dualize this as well. Is this clear? And I can do the same trick. What is nice is you see here is because I had this separability, this term in the objective also separates into the 2 subproblems. Right? Let me highlight this again. In particular, the 2 subproblems you would solve is one with this term and this other term. So you see the problem separates. Okay? So, okay, so if I add these separable redundant constraints, I definitely retain decomposability. But all of this for what? Am I going to actually get something better on the dual side? On the primal side, I've not changed anything. But do I get something better on the dual side? That's the question. All right. And so first, a negative answer. Right. So we know that we've added redundant constraints. So on the primal side, nothing has changed. But has the dual changed? Do we get a slightly better bound than what we had earlier? And the first negative answer is, unfortunately, in this example, nothing will happen, because the result is that if either of these alpha 1, alpha 2 functions is affine, then in fact you will not get any improvement. Okay? And so if you see in our example, the first function was the sum of the first two binary bits. This is just a linear or a affine function. And so therefore, this proposition says dual opt dash is equals to dual opt. I've not any progress. Okay? But then I ask myself, okay, is there any hope of adding these redundant on the primal, which doesn't change the primal at all, but now the dual gets changed? Is there any hope of improving the bounds? So clearly this proposition says that both these functions have to be nonlinear to get any improvement. Okay? And so here is our proposed nonlinear constraints. Okay? In some ways it's quite silly constraints and maybe not very practical, but I'll talk about that later. Or I'll talk about that after my talk. Usually that's what I do. What I'm going to do is I'm going to say, this string of 10 binary vectors was equal to this string of binary vectors. One implication is the first variable in this left-hand side and times the second variable on the left-hand side is equals to the first variable on the right-hand side times the second variable on the right-hand side. Right? So in particular, what I can do is I can select a subset of binary variables and then multiply on the left-hand side problem, take the same set of binary variables, multiply it on the right-hand side. Because each of them individually had to be equal, their product had to be equal. Okay? And we call them M constraints because this M is a monomial. Right? So basically, we look at monomials on both sides, and we pick a monomial and then equate them. As an example, if I take variable 1 and 2, I take their product on the first problem, take their product on the second problem, and I equate them. Okay? And just a side remark here, I'm going a little slow, so maybe let me skip this. But basically, this looks, feels, smells like Shirley-Adams or RLT, but it's not the same. Okay? And we can talk about it more later. Not only in the construction of what these terms are, but also RLT is all about linearization. We are never going to do that. So it's really a different thing. What's the result? Result is if you take all the monomials on the left-hand side, so there is for every subset there's a monomial, and you take the products, and you add all of these redundant constraints, and now take the dual, Lagrangian dual, there is no gap. Is the statement clear? Okay? So I would say this for me was the greatest insight. I didn't know this, but you can add redundant constraints to your problem, which are completely redundant to your primal problem. But now when you look at the Lagrangian dual, you actually get much tighter bounds. Okay. So let me actually try and sketch the proof. The proof that I'm presenting here is not in the paper, so that's, thanks for inviting me. Just kidding. But it's an easier proof. It's not as general. But it has some very nice points because it will allow us to generalize these things to not just MILP, sort of MI nonlinear also. Okay? So let me just quickly sketch a proof of this. The proof it's literally 2-3 lines. So you'll see it's really straightforward. So I'm going to define something called as the response function. What do I mean? For each of these two problems, there are these common variables, the string of 10 vectors that were supposed to be equal. So if I fix the string of 10 vectors to some value, which is in this bold red, and then I solve for the rest of the problem, what is the value? If you're thinking stochastic programming, think about it as I fix my first stage variables, and then I ask for this scenario, what is the optimal objective function value? This is what I'm calling as response functions. Okay? And I'm sure there's a term in stochastic programming for this, but I had to rebrand everything. That's how the world works these days. All right. Okay, so I have this response function. For simplicity, I'm going to assume that the response function is always feasible and bounded. The feasible is really not very difficult to take care of in this particular kind of proof. The bounded this proof, I really require bounded. For the unbounded case, the proof that is in the paper goes through. Okay? But here, for the simple proof, I just assume boundedness. But once I have this bounded, here is the key observation for this sort of this skewed dual result to go through. Sorry. What is this? This can be anything. I don't care. This could be any crazy function here. But it's a function that's defined on 0, 1 points. Because remember, the state variables we had was 0, 1, this vector of 10 variables. And since I have assumed the problem is feasible bounded, basically on this 2 to the n cube, I have assigned some numbers. It could be any arbitrary numbers. It's well known that if you have any function on the 0, 1 cube, you can represent this function just using a monomial basis. Right? You can represent this function as some coefficient times the linear terms plus some coefficient times the degree 2 terms. Plus, this is very easy. This is a simple exercise. You think about it for 10 seconds, you'll realize you can do that. So in other words, this crazy response function, which I have no idea about, I know that there exists some weights corresponding to every subset such that this function can be represented in this way. Is this clear? Okay, and now we are there. All right, so let's use this mu star for the coefficients for the response function of the second block. The proof is a little asymmetric between the first and second block. So this is our primal value. This is our updated Lagrangian dual. Just because of the construction of dual, we know that this inequality holds. What is this dual? This is maximizing over the dual multipliers, right? We are trying to best penalty for these monomials being equal on both sides. And this is the response function and response function. This is nothing but the original IP. I just write in the language of response function. This is the response function of the first variable, second variable. And we are not enforcing x1 equals to x2. Instead of that, we are putting these penalty terms. And this is the inner minimization of the Lagrangian problem, so this is exactly the Lagrangian dual. Good. But what I'm going to do is I'm going to fix a value to these mu's. The moment I fix that, I was trying to maximize with respect to mu, so now this number is at least as large as this fixed value. This is clear. All right? But now I expand this term. What do I observe? Well, what I observe is that I'm using this mu for the second response function. So this first term is the second response function applied to the first set of variables. And the second term is this second response function applied to the second set of variables. But that is precisely the term here. I love canceling. That's one of my favorite things in math. If you can cancel, you're a happy person. I cancel. And then what am I left with? I'm left with minimizing first response function to the first variable plus second response function to the first set of variables. But that's just basically saying sum of the two response functions applied to the same string of binary vectors. And so this is opt, and so this is true. So that's the proof. Literally, 2 lines. Okay? Any questions? Comments? I can't count, sir. All right. Very good. So let's move on. So, and as you can see from the proof, I did not use the fact that these subproblems were MILPs. They could be any arbitrary nonlinear objectives, any crazy sets. The only thing this proof used was that each of these subproblems were feasible and bounded, and the fact that the common variables were binary, because that's why I could use this suitable monomial construction. Okay? So you had an MINLP, your favorite stochastic, 2-stage stochastic MINLP, as long as everything, all the scenarios were bounded and feasible, and your state variable was binary, this would go through. Okay? All right. But of course, you're sitting there and wondering, and you're being polite, and I know that you have to be polite many times during this talk. Yeah, this guy's adding like this exponential number of terms, right? Isn't he? You're looking at a neighbor, isn't he? That's what he's doing, right? Yes, I'm doing that, right? So of course you ask, is this tractable? Is this practical? And I don't know the answer to that. I never answer those questions, but I'll try. The first thing you can ask is, okay, for getting the strong dual, I need to add this exponential number of monomials on both sides, right? So I have to look 2 to the n subsets, 2 to the 10 in our example of 10, 2 to the 10 monomials, and equate them all. That's the only time I get guarantee of strong duality. But what if I don't add all of them, right? What if I just go to all the degree 2 monomials? Or 3, I'm sure, is the favorite prime number for everyone in this room, so we go to degree 3, right? What happens? So it turns out we can do some analysis and say something about that. And the other thing is, this bullet point is, I will show you that this method can be reinterpreted in a different way, and it's very close to an algorithm that was invented by Professor Shabir Ahmed, and they're very close parallels. And there might be a linkage to how you can actually use this practically. All right, so let's do that. So we cannot analyze this in general with this fixed degree, but we can analyze them for packing and covering IPs, but those are very nice classes of problems, fairly general. I'm going to write so packing problem, as you know, A is non-negative, less than or equals to B, A is non-negative, greater than B is covering. Usually packing is written with max CX, but Jingye, who, as I told you, did all the work, doesn't like max for some reason. So we write this as min. It just helps writing some of the results, okay? So it's written in this slightly convoluted way, min of a minus negative function. And so here's the result, what we can prove. For the packing, we need some more assumption, which says that the projection of the feasible set is equal on the two things. But this is, for packing, this is not very difficult to obtain. And in the world of stochastic programming, for example, this is what is called as the full recourse assumption. So this is not a big deal. But under that assumption, the packing case, in the covering, we make no assumptions. Skip all of this. Let's look at the graph. Basically, what this says is, this is a 10-variable problem. For the packing problem, if I added degree up to 10, there is no gap. Okay? And basically, if I go to degree 2, in this example, this is how this curve goes. This is what this is saying. Okay? And so, in other words, what this says explicitly is, at least for packing and covering, we can show that if you change the degree, you explicitly get improvements. Okay? What is not nice about this analysis is that, in a sense, what you see is it's kind of flatter in the beginning, and it kind of curves down quite a bit for packing. And similarly for covering here, it's kind of, yeah. So, but for a lot of these hierarchy type results, the best you can typically show is that you make little progress and you make a lot of progress right at the end, and that's sort of what's happening. Empirically, this is not true, and I'll show you some numbers. Okay. All right. So that is one. So you don't have to add the whole exponential. You can go to a fixed degree. This still makes the subproblems very difficult, for sure, but there is some hope, and you can get something. Here is another interpretation of this result. I think I'm going to skip the proof of this, mostly because the slide doesn't look nice also. Okay, good. So here's another interpretation of this result. So as I said, remember, what was our first proposition? We said redundant constraints, separable redundant constraints are not useful if any of those two functions are linear, right? That's why we said the most natural was to do polynomials, right? But there are other kinds of nonlinears we can look at. And here's a very specific nonlinear function I want to look at, which is an indicator function, right? This says pick a binary vector v, and that's why we have vertices of the 0, 1. That's why we call them v constraints rather than m constraints. And then this indicator function is just saying, if this string of vector v and u are equal, then it's 1 or 0 otherwise. Okay? And now you can add, this is a nonlinear function, and you can just add this redundant constraint. So these two vectors have to be equal. Like a very weak version of that statement is saying that is this vector equal to this vector, and is this vector equal to the same vector, and if they are, then it's 1. Right? And why is this a reinterpretation? Because actually, what is an indicator function? So saying that a binary vector is equal to 1, 0, 1, it's 1 if it is equal to this, or 0 otherwise, it's just, in some sense, this expression. And this is just saying these two are equal. So what this equation is doing is nothing but linear combinations of your monomials. So it's really, you're not changing anything. It's just reinterpreting the same monomials in a different way. And so for free, as you can see, this implies that if you added all the 0, 1 indicator functions, you will get strong duality. Okay. But let me say why this interpretation might be a little bit more tractable computationally. So, all right. So here's a key observation. It's not very difficult to prove that, let's say you were trying to solve this Lagrangian dual using subgradient algorithm. At every iteration of the subgradient algorithm, what you can prove by looking at the structure of the subgradient is that these penalty terms, they're exponential, right? There's 2 to the n 0, 1 vectors, indicator functions. But actually, the number of penalty terms that are non-zero will only increase by 2 in every iteration. So let's say you start by just solving the 2 subproblems with penalty terms as 0. So you just solve the 2 subproblems. Then you look at the optimal solution, you construct the subgradient, and you take a step. Only 2 of these indicator functions will get non-zero entries. And every time, you will add 2 more. So as you run the algorithm, very few of these duals are actually non-zero, at least in the beginning. Okay?
I mean, there exists a solution where you have to change it most, not for every subgradient.
Yeah, not for every subgradient. Fair enough. But in a reasonable setting, because, yeah, you can pick one where there will be one. Exactly. And so, in a sense, I imagine that if I have to actually take 2 to the n steps to solve this, I would never do this, right? So I would hope that I can take a few steps of these subgradient steps and actually get a very good dual bound. Okay? And so then the question really is, I do have an exponential number of terms here, but really very few of them are non-zero. So how do I solve for it? And the reason I will try and present this in a very specific way. So let's say this squiggly v is a set of these mu's that are not zero. Oh, that's a typo there. That should have been mu. So mu v's that are not zero. What you do is you remove the guys that are zero, and you solve the remaining problems. This can be done in the language of stochastic programming with no good cuts. And for the guys that are not zero, you kind of compute these response functions one time, and you just add this. So in other words, there is actually a reasonable way of implementing this if the number of penalty terms are not too many, and take the minimum out of this. Okay? I just mentioned this because we're actually going to do some implementation of this later, and this is what we did. Okay, so now I want to change gears a little bit and go from this sort of toy setting to a general IP setting, okay, and discuss why these results will carry through. All right, so how do I do that for a general setting? So a general IP kind of looks like this, right? So I have linear objective, linear inequalities, X6 mixed binary. And what we have to do is we have to use the notion of what is called as the intersection graph of this problem. What you do is you look at this A matrix. So this is sort of supposed to be my A matrix. And wherever there is a dark gray, that's where there is a non-zero entry. And wherever there is nothing, there is a 0 here. Most real-life IPs are very, 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 very sparse. Okay? I think many years ago, with not the latest version of MIPLib, the previous version of MIPLib, we just ran through what the sparsity is, ignoring the bound constraints, because those are very sparse. And I think average sparsity in MIPLib instances is like 0.06% or something. Really very sparse. Okay, real life problems are sparse. You don't have a problem where everything is dense. You have some transportation constraints, and then supply, some risks. They're all in blocks, and there are lots of zeros. And then what you do is you construct a graph here. You construct a node for every variable, and construct an edge between these two nodes whenever there's a constraint. So for example, in this constraint, here there's a non-zero with variable 1 and non-zero with variable 3. So you connect an edge in this graph between 1 and 3. This is the intersection graph. Okay? And then you do something with this graph called as the tree decomposition, which I will not go in too much detail, but it's a very, the most intuitive way of thinking about this tree decomposition is if your original graph was tree, the tree decomposition is the tree itself. Okay? It's a way of taking the nodes in your graph and putting them into bags and connecting these bags in a tree with some very nice properties. Okay? And so we'll do a tree decomposition. That seems the right natural object in this setting. But here's how we'll now do the Lagrangian decomposition. And this is a little bit hand-wavy. Folks who have not seen tree decomposition before, my apologies for that. But for folks who have seen it, this will be very clear. So I have my tree decomposition. I have bags with different variables. Okay? For each bag, I'm going to write a local IP with objective function on those variables and constraints for each bag. Because of the construction of tree decomposition, you would consider that any constraint you had in the original problem would be represented in some bag. So you'll not miss out on any constraints. And what you'll do is, on neighboring bags, there'll be some variables that are common. These are going to be my coupling constraints. And for these coupling constraints, I will add the additional polynomial or indicator function redundant constraints and dualize those. Okay? And once you do all of that, it turns out you will get strong dual. Okay? So a couple of remarks here. There's a very famous thing in integer programming that's related to tree-width, which says that once you do some tree-width decomposition like that, and you write some sort of an extended formulation of the convex hull for each of the bags, and you equate variables in the right way, you get the convex hull of that. So when we got this theorem, we thought this is just a reproving of that theorem. Turns out this is a bit different. I think the best way to think about why this is different is, let's again take our string of 10 vectors, and let's assume those two problems had another 1,000 variables. What tree-width would say is that you would look at 1,010 IP, you would write a 2 to the 1,010 extended formulation for each piece, and then you'd equate them. And this is an LP. After this, you don't have to do any work. Here, what we are saying is, you have to write the 2 to the 10 sort of extended formulation dual variables, but it's not an IP formulation. You still have to do the Lagrangian dual algorithm and run through it and get the optimal solution. Okay? So it's a little different in flavor. Okay, so this is a work of art, I think. Yeah, I'm going to skip this horrible slide. But basically what I will say is that all of the stuff about packing and covering that I told earlier with the simple toy, you can extend some results like this in tree setting. And if you're really interested to know, this is somehow related to looking at the bags and looking at subsets of variables, and then doing some sort of fractional coloring number of this in this tree. And then the approximation bounds you get with the degree depends on this somehow. Okay? And the subset of variables you pick depends on the degree of the polynomial, something like this. Okay, let's skip this. I think this is a far more interesting thing. So this is sort of saying that the M Lagrangian theory kind of goes through with this general setting. So let me tell you about V Lagrangian. The V Lagrangian is actually particularly suitable for stochastic programming, two-stage. So here's the setup. With two-stage IP, X is my first stage variables, Y is my second stage, I is the scenario, second stage variables. I have S scenarios, and I'm thinking of a random two-stage problem where it's a packing problem, everything is non-negative, and each of the entries are IID 0, 1. Okay, it's a random IP. Each of these second stage constraints have M constraints. And the right-hand sides have to be of some formula. It's fairly general, but it's not totally general. What you can prove is that if you start with solving these S scenarios completely separately, right? You make a copy of your first stage variable for each of these S scenarios, you solve it, you take the optimal solution, look at the subgradient, you update the penalties of these indicator functions, and you keep repeating this, right? So the question is, how many such iterations do I have to do to converge to the optimal bound? It turns out in this roundness setting, what you can show is that the number of iterations to get an additive epsilon gap looks something like this, which is ugly. But what is nice is that the number of iterations with respect to the scenarios, you see, is basically, forget about this alpha. This alpha is basically M. Okay, it's n to the m, and you cannot avoid that. There are arguments to do that. It says it's basically n to the power square root log s, which is a really small number in number of scenarios. Right? If you just sort of solve this problem, it's 2 to the ns, right? That many variables. So it's exponential with x in some sense. But here the growth is only in the exponent is not s, but it's square root log x. Okay, so and I won't have time to talk about how we prove this, but basically you use techniques from convex optimization because you know how subgradient converges to epsilon additive solutions, how many steps you need. And it turns out the result is something to do with how large are the optimal dual solutions. And so this theorem is nothing but stating that for these random sort of packing two-stage problems, it turns out that the penalty weights that we need are not too large. That's what you have to prove. So that proves this theorem. Okay, sort of, like I know Jim has told me many times, oh, these Lagrange really work very well. This is sort of trying to get towards that to say that, yes, somehow, at least in some random setting, doing slightly more complicated things, because you're doing very few iterations, you're putting very few penalties to get convergence. Okay, so I'll not speak any more about this. Let me talk about some computational results. All my computational results are preliminary. I've never actually presented final computational results in my life. Okay, computational results. So here's what we did. We took stable set, which is like a graph, And then you know what a stable set is, right? You pick nodes so that there's no edge between them. You want to pick as many of such nodes. And so the way we did it is we did stable sets on 100 nodes, and that's the single block. And each block was partitioned into 33 nodes, so like 9900. And we constructed two types of problems. This is what would be a stochastic program where you can think about some 33 nodes are present in each of these scenarios. Once you pick this, you can select the rest of the stable set in this. And this is a path where the 33 nodes of the first block are the same 33 nodes as the second block, but the last 33 nodes of the second block is the first 33 nodes of the, okay? And in these cases, the tree decomposition is trivial, like this is already path, this is a star. So I'm kind of building the tree for myself in a free way, but now I can use this general M and V. What are the things I applied? So classical Lagrangian. We definitely can't go exponential. We do just quadratic Lagrangian because the subproblems are quadratic. We do this vertex Lagrangian, which is what I told you, which is like indicator function penalty. And then we implemented this algorithm by Shabir, which is like scenario decomposition. Let me just say this algorithm in 30 seconds. It's very elegant, very clean. You're trying to solve a stochastic program, two-stage stochastic program where the state variables are binary. Here's what you do. You solve them individually with separate copies of these state variables. You find the optimal solution for each scenario. You evaluate them for the whole stochastic program, right? You throw away these solutions and just add cuts that say, don't explore these solutions for each of the scenarios, and then again decomposibly solve. So it's a very nice, it's clear the convergence occurs, it's a decomposable algorithm. And I think the difference between this algorithm and the vertex Lagrangian is that we don't add cuts and remove those points. What we do is we put penalty on these points. I think that's the way to interpret the V Lagrangian as a sort of a generalization of this SDA method by Shabir Ahmed. And so here are sort of the results. The Lagrangian dual, by the way, we had to use bundle method to solve them. So Groby, 1 thread, 10 thread. So this is the star, which means this is like the stochastic programming instance. And we ran them for this is 20 minutes. And you see that the V Lagrangian here gets you the best bound. The quadratic is also quite good with the quadratic monomials. You see that the Lagrangian does worse. Of course, Groby does much worse because Groby has no knowledge of, even when we give 10 threads, it cannot really decompose. And this algorithm actually doesn't do that well in these instances. What should I say more about this? There was one more thing I want to say, but okay, come to me. And this is the path instances. And in the path instance, this V Lagrangian is really not the right way to think about things, so it doesn't work. So we do the Lagrangian and quadratic Lagrangian. And you see here the quadratic Lagrangian is significantly better than Lagrangian and Groby, which of course doesn't know anything about the decomposition. Is it a fair comparison? No. There's a huge literature in stochastic programming. We've not implemented the most fancy stuff. We've literally implemented the Lagrangian as I told you here. The other comment I would say is it's not clear, for example, here, that you close the gap, but if you see here, yeah, this second is slightly less because there were some instances where actually you got to strong duality just using the quadratics. Okay, and we have examples where we showed that the Lagrangian has gap and already the quadratic root cause gap. Okay. I have a choice. I have 10 minutes, so I can go to the next topic, or there's a fun thing that I wanted to show Jeff. This is only for Jeff. Okay, but Jeff wins. But Jeff wins. So Jeff wins. All right, so here's a fun detour. Hello, neural nets. I have no understanding of machine learning at all. But since everyone seems to do it, I thought maybe I should try, get my hands dirty. It turns out this interpretation of Lagrangian dual has a very nice way and connection to sort of function approximation. That's what these machine learning tools are doing, right? And they've been used already in stochastic programming, at least to my knowledge in a certain way, but I'm going to use it in a slightly different way. Okay, so let's revisit our proof of strong duality. We had some arbitrary nonlinear function. We have these two feasible regions. We have these coupling constraints. And what did we say? We constructed this response function, which is we fix the value of this x, and we solve the remaining problem. This is the response function of the second subproblem. And basically, if you look at the proof, what we did, basically it says is that you take this coupling constraint, and replace it by saying the response function applied to the first set of variables equals to the response function. Second problem applied to the first set of variables equals to response function of the second problem, again applied to the second set of variables. This is an implied constraint because x1 is equals to x2, and I'm applying the same function. If you just replace this constraint with this constraint and you dualize, you get the strong dual. That's what the proof is saying. All right? And so now you see where I'm going with that. If I knew what the response function of the second problem was, I can write this Lagrangian dual and then get a tight dual. But of course, I don't know this response function, right? That's part of solving the whole problem. But hey, because we're not adding any cuts, we're not changing any feasible regions, we're only updating the objective, who cares if I have the right function or not? I can just use an approximate function. It's still a relaxation. And so what I'm going to do is very subtle hint. I'm going to use an approximation to this response function that I'm going to call as the NN function. Right? And so I'm going to write this relaxation. This is a relaxation by definition because this was implied by x1 equals to x2, and this is just, yeah, so this is by construction, this is a lower bound, but I don't have to use this response function. I just have to use an approximate function. Now, from what I know, and maybe, and again, there are experts here who will tell me better, people have used 1/2 of this in literature. In particular, there's a very nice paper by Merve, who's from here, and co-authors, where they say, just take the response function of the second problem, approximate it using neural nets, and then you solve the problem with the first problem plus the approximation of the second problem. In other words, in stochastic programming world, you take each of your scenarios, you approximate the second scenario function using neural nets, you add this function to your first stage problem, and you solve the problem in first stage, and you get good solutions. And they've shown they recover very good solutions this way. So they are not solving this complicated second stage problem, they approximate it using neural nets. But this is only a method to get primal solutions. It gets feasible solutions with no guarantees. But now, if you think about it in this sort of Lagrangian framework, using that same neural function, you just solve, like instead of 1, you solve 2 subproblems, one corresponding to 1 here and the other to 2, you get a lower bound. So using these approximations, which apparently are called as optimization proxies, not only can you get these good primal solutions that people have used, you can actually get dual bounds. And so with this master's student, let me skip this, I don't have the time. Basically, oh, come on. We did this on this toy kind of problem, right? So about 60 variables in each block, 15 common variables. Literally, this ran until yesterday, I was telling Carla. What we do is basically, yeah, we solve these 2 problems separately. We get these optimal solutions. Around these optimal solutions, we compute some response functions. We perturb these optimal solutions and compute some response functions, train neural net, solve the Lagrangian dual, again in a separable way, get an optimal solution for this optimal solution. Again, around that, search the response function, update your neural net, and just iterate. So we did 5 iterations of this. The problem is, I should probably tell you what the problem, though, is. I mean, we had to make it difficult to see if, on easy problems, Gurobi will definitely beat us. So this is like a non-convex quadratic IP. That's the objective on each of these 2 terms. And the first 15 are equal. And I was pleasantly surprised that actually you can make quite a bit of improvement. We ran Gurobi on these instances for about an hour and a half. The cap was about 9%. And these are the topologies of the neural net we used. So K is I should have used N. This is the number of your common variables, so that's the first level. This, if you see just one number, that's, there's 2 log K in the second level, and there's ReLU activation function. If you have two arrows, then there's 2 internal layers. And so these is results. And it's not surprising that as you use more complicated neural nets, the results are much better because you probably approximate the response function much better, but at the cost of higher time. Okay? All right, I think I will skip the second dual. My apologies, but please feel free to reach me if you want to talk about the second dual. Let me just finish here because I'm almost running out of time. So the biggest takeaway for me personally from this project was Lagrangian duals are not tight, but you can add redundant constraints. It will change nothing in your primal, but the dual bound will improve. What we showed is that effectively you can get strong dual. You can close all of the gap, but there is a trade-off, right? There's no free lunch. You get complete strong duality, but at the cost of solving much more complicated subproblems, because now your objectives have these polynomials in them, right? So this is much more expensive. You can, simplify and get a little bit of maybe improvement by not going all the way to exponential, but like quadratic number of terms. But honestly, those experiments are a setup, right? You could see that because I have 100 variables, right? So each block has only 100 variables. On 100 variable problems, Groby can solve a quadratic IP. If those blocks were of size 1,000, I don't know what to do, right? So I'm not saying this is an answer, but it is kind of very interesting that you can. And in fact, in some empirically, we closed the complete gap in quadratic itself. You can try the V-Lagrangian, which I really think does, with the right implementation, can be scaled. The tree decomposition machinery helps you to generalize from the toy problem to general problems. I certainly think that especially with V-Lagrangian, the preliminary computations are quite encouraging. And as I said, you can now, once you think about this framework, you can use these optimization proxies not only to get very good primal solutions, but you can actually also get dual solutions. One thing that I'm really thinking about right now is all of this, at least the theoretical results depend on the fact that these common variables are binary. But they could be continuous, right? So for example, one of the questions that we are looking at right now is these response functions. Let's say my problem was a QCQP, and this is a continuous variable. If I fix these variables, what is these response functions looking like, right? And there are theorems in algebraic geometry, which I have no idea that I'm trying to learn, which says, oh, the optimal solutions, it turns out, are also polynomially representable with degree so and so. But once I know that, then I know I can add monomials on both sides up to a certain degree, and I'll get strong duality, for example, right? So that's the direction I'm thinking about. And I think maybe this is an amazing set of slides that I'm sure you are following as I do it. But let me stop here. Yeah, there's a nice picture you missed. Yeah, and thank you very much.
Are there questions?
I have many. All right, so I'll ask my first question. The other ones I'll ask later. So going back to this result, which was like your first result where about when you get improvement, and if you like the functions in the two-block case, if they're both fine, it's sort of clear that you can't improve on the Lagrangian for sure. But the result is both of them have to be non-affine.
Yeah.
That's interesting to me. But then, so what if you have 3 blocks?
So I think so. The way we think about it,
you have to have two. You have to have 2 non-affine functions,
so it depends on
all of them have to be non-affine? I guess that's a question.
No, that's a great question. So first of all, if the 3 blocks are aligned in a triangle, then I don't know how to prove strong duality, right? So I would have to do some sort of tree decomposition, and the 3 blocks have to be assigned in some sort of a path.
I see. Okay.
And then for each pair, I have to do, they'll be equal.
Okay.
And that's what the general thing does. It does the tree decomposition, and then across edges of the tree decomposition, you look at the common variables on the 2 bags, and there you.
I see.
Yeah, exactly.
More questions? You want to ask one more? Just a clarification question. So you have looked at the case where you add monomials up to a certain degree, but can you understand can you generate new monomials that are needed to improve?
That would be very nice. We don't really understand that at all. That would be super nice. It would be super nice if I allowed few high degree terms, but then that's all that's needed. I just have to add like a fixed number. That would be super cool.
A kind of separation.
Yeah, separation. Yeah. That would be. We thought about it a little bit. We didn't make any progress, but something like that would be super cool. Yeah. This has to be true. The question is, can you find?
Maybe it's a super hard problem to solve.
It's to find.
So,
but this has to be somehow true in some sense.
Okay.
It's like intuitively. Yeah.
Okay, so then let's thank Santanu again. So he claims that when you have essentially, so you talk about the intersection graph and then you do the tree decomposition on top of that. but he told me, I don't remember what is his, probably it exists. There is another more precise, stronger tree decomposition that you can define.
Okay.
Where you don't, in the intersection graph, you have an edge whenever two variables appear in the same constraint.
We need to get a photo.
Oh.
Okay. But yeah, just ask Alberto
Okay.
about this
Okay, I will do
decomposition.
that. Okay.
Maybe
Okay.
you can get a better.
Okay.
I need you to be in the photo too. Just right here, everybody. Just, yeah.
Shantanu in front.
Okay.
Can we make a pyramid? Shantanu's had been in my pyramids too.
Stand up straight. There you go. That's good. Okay, now maybe
Thank you.
one of you alone, just stand. You alone, just
Okay.
stand like you're. Yeah. Just put your, just stand like this.
Oh. Oh.
Great.
Oh.
Is your lap? Is it gone?
We can add it.
Again. Sorry, I'm taking
That's okay.
ownership of you.
Yeah. Please. Yeah, just push it in.
Yeah, you need the.
Sorry, I can't. My eyes are really bad. Yeah.
Yeah, but you'll need
To turn it on again.
No. Sorry for the pointer.
No. This worked. That's okay. No. That's
But I
okay.
didn't want to
I
interrupt.
yeah. No. No.
You'll be glad later.
No, I'm taking him to lunch.
So you're not done.
Is Alberto
Yeah, he's joining, but we will. So let's work together, and then I switch to the back.
okay? Seamless. Make it seamless.
Yes, seamless.
We can start
If
talking
that's
in
too much
Italian.
work, we don't have to.
No, I will not come. I need to get the time.
Did it?
Sounds good.
I have to go to the display. I have to go to display, and I have to say.
Go to Steinbach's and get the
I think.
reservations.
How did I do it?
But it will be fine.
It will
We
be
arrive
fine.
late all the
All
time.
right, sounds good.
No, because I need to get the car.
Oh, you need to
Oh,
go,
it's
But that's okay. We can.
it's we can do the trees.
You just stand.
Yeah.
And then we'll just.
Yeah. Trees are good. They're better than my slides, anyways. Yeah.
Well, you have trees on your slides also, right?
Yeah, I did have trees on my slides. That's true.
Gonna do that in the background. And then I'm gonna do. Sorry. Come on.
It's all right.
Come on. Why is it doing that? Sorry.
That's all right.
Okay. Good.
Thank you.
Thank you, Jay.
No good for doing our propaganda tour. This is crucial.
Yeah, I'll ask him about that. And it's kind of interesting here. Somehow you don't really care about the tree decomposition is the smallest tree, back size, because in a sense the exponent is happening about common things across the edge. You want those to be small, but of course you also don't want the backs to be too large, because then your subproblem is too large. So it's not clear in this case the right decomposition is really the tree decomposition. It's kind of like some weighted, you don't want the backs to be too large, but then you don't want the variables across an edge to be too many, right? Yes, it's not clear. Yeah.
But yeah, you can ask him. Maybe the bags could be smaller. At least the subproblem.
Yeah, I should know. Oh. Okay. All right. I will. Yeah. So I think I'm done sort of at 4-ish. So okay, and then we can talk about it. All right. Thanks, Jeff. Yeah.
I could take your bag up to my office. Are you going to go?
It would be best because I will need to go home in the afternoon.
And then, also look at the bathroom if you need a break.
I think I'm fine now.
All right, sounds good. Is this your number?
765-426-3593. Yes.
So I'll be in touch.
Yeah,
I'll
yeah.
maybe see you sometime.
Yeah. I'm sure someone can open the door worst case.
Yeah.
But I can also take it, Jack. I mean.
No.
This is also
Are you sure?
Shantanu's.
This is okay.
Okay. Thanks, Jim. Thanks very much. Yeah. If you have any comments, I don't know.